FutureSim, replaying world events to evaluate adaptive agents. If you're an ML engineer working on agentic workflows or test time compute, you really need to hear this. Current AI benchmarks completely fail to measure how models actually adapt to new information over months in the real world. FutureSim solves this by placing agents in a simulated 90-day time lapse. So from January to March 2026.
Right, and it feeds them daily news and asks them to predict the future. And the results, honestly, they're highly polarizing. GPT 5.5 completely dominates with a 25% accuracy and a positive Breyer skill score.
But then you look at a lot of the other frontier models, especially the open weight ones, they perform so poorly at calibration that they actually score worse than making no prediction at all.
Exactly. The paper basically proves that for long horizon test time adaptation, raw model intelligence is just not enough. Success actually requires agentic search, continuous memory to prevent hallucination drift, and, really meticulously designed agent harnesses.
We also learned that scaling test time compute significantly improves calibration, but it definitely hits a hard ceiling. So welcome back to AI Paper Podcasts, where we unpack the architectures driving the frontier. Let's just get straight into it.
Yeah, the performance gap between the models here is just staggering. But the most important takeaway is why this benchmark was even built in the first place.
Right, because we rely so heavily on static benchmarks.
Right, things like ARC, AGI, or vending bench. And they're giving the industry this massive false sense of security about what these agents can actually do out in wild, unconstrained environments.
Let's dissect that false sense of security for a second, because we see models crushing coding and logic leaderboards every single week. Why aren't those existing metrics enough to tell us if an agent is genuinely adaptive?
Well, think about the nature of a coding benchmark or like a logic puzzle. The entire state of the world is contained right there within the prompt. The rules of Python do not change while the model is writing the function.
Right, they're completely static.
Exactly. But real-world deployment requires adapting to societal, economic, and political evolution over time. Information arrives sequentially, facts change, and previous assumptions get invalidated. FutureSim tests that exact sequential adaptation.
And the environment itself is incredibly minimal, right?
Yeah, it essentially offers only two actions to the agent. First, submit forecast, which registers or updates a probability distribution for a specific question. And then second, next day, which just advances the simulation forward by 24 hours.
It's essentially like locking the AI in a room, setting a calendar to January 2026, and just sliding a daily newspaper under the door every morning.
That is a perfect way to picture it, yeah.
And then you're forcing it to place bets on world events based only on what it reads in those papers. But stepping into the shoes of an ML engineer, my immediate concern here is data contamination.
Oh, absolutely. The cheating problem.
Right. If this simulation is running today, how do you stop a coding agent like GPT 5.5 or Claude from simply writing a bash script to ping the live internet? Like, what stops it from scraping Wikipedia and quote-unquote predicting the future by looking up historical facts?
The researchers definitely anticipated that exact bypass. So the agents are completely sandboxed. They are cut off from the live internet entirely. No curl commands, no web scraping, no external API calls at all.
So how do they get the news?
They only have read access to a highly controlled local offline folder. The simulation basically maintains a repository of news that updates daily based on the simulated date. So the agent only has access to the information published up to that exact day in the time lapse.
Which means the researchers had to build a massive, perfectly sealed data set to act as that daily newspaper. You couldn't just feed them raw internet data without accidentally spoiling the future.
Right. Building that offline environment required some pretty significant infrastructure. They sourced 330 free-form questions from Al Jazeera articles, mostly focusing on global events.
And they filtered these questions pretty ruthlessly, I imagine.
Very ruthlessly. Any question that was too easy to guess using web search data capped at June 2025 was just removed. They wanted to guarantee that the agent couldn't rely on its pre-training weights.
Or even just obvious historical trends.
Exactly. True, dynamic forecasting based on new information was strictly required for this.
And to simulate the internet within that closed environment, they had to host the entire search corpus locally.
Yeah, they downloaded 7.36 million articles from Common Crawl News, or CC News. And to allow the agents to search this offline database effectively, they set up a LanceDB hybrid semantic and keyword search.
Powered by Qwen3 8B embeddings, right?
You got it.
Let's pause on that architectural choice for a second. Why a hybrid LanceDB setup with Qwen3 embeddings? Why not just use a standard SQL database or a pure vector search?
It really comes down to the dual nature of fact-finding. If you rely purely on keyword search, the agent often misses critical context. Like, it might search for U.S. election polling and totally miss an article titled Voter Sentiment Shifts in Swing States.
Ah, I see. But if you rely entirely on pure semantic vector search.
Then it often fails at exact entity retrieval. It might understand the semantic concept of winter sports, but completely fail to retrieve the specific string Emma H'er when it's searching for a skier.
So the agent really needs both. The exact keyword matching for specific names and data points, and the semantic search to understand the broader cultural or political context of an event.
Precisely.
But hosting 7.36 million articles locally and running custom embeddings, I mean, that is computationally expensive. It's highly complex. Wouldn't it have been infinitely easier to just use a live search API and restrict the date parameters?
You would think so.
Like you could just query a search engine and append before 2026 0130 to the string.
So the researchers actually attempted that first using the Brave Search API, and it resulted in a catastrophic failure that perfectly illustrates the problem with live APIs and chronological simulations.
Oh, wow. What happened?
Well, they had a question about the Milan Cortina Winter Olympics, specifically predicting the country of the women's downhill skiing silver medalist, and that event took place on February 8th.
Okay, so in the simulation, let's say the date is January 30th. The agent runs a search using the Brave API, filtering strictly for articles published before January 30th.
Right. The API processed that date filter and returned a fandom wiki page that was originally published on January 9th. So on paper, it passes the filter.
Wait, I think I see where this is going.
Yeah, here is the fatal flaw. The text snippet dynamically generated by the API included updated text from the live web page explicitly listing the February 8th winners.
Oh, no.
Yeah, flat out stated Emma H'er of Germany won silver.
That is amazing. It's literally the Biff Tannen scenario from Back to the Future, getting his hands on the sports almanac. The search engine just bypassed the temporal integrity of the simulation.
Exactly, because live APIs continuously update their indices. They dynamically generate snippets based on the newest available crawl, regardless of the original URL publication date.
And that leakage completely compromises the benchmark. You can't measure true test time adaptation if your environment is accidentally leaking the ground truth through metadata or dynamic snippets.
Right. That single failure proved that the frozen local CC news corpus was not just a preference, it was an absolute architectural necessity.
Okay, so with the sandbox perfectly sealed and time travel enforced, we can finally look at the leaderboard. But before we talk about who won, we need to discuss how they actually kept score.
Because they didn't just measure binary accuracy, they used the Breyer Skill Score, or BSS.
Right, and BSS is a fundamentally different metric than standard accuracy.
It is. It measures calibration, so how well the model's confidence aligns with reality.
It's basically the difference between taking a multiple choice test and setting the odds for a casino. If an agent says there is a 99% chance that a specific event will happen and it doesn't happen, the Breyer score severely penalizes that agent for being overconfident.
Exactly. A BSS of 1.0 is perfect confidence in the correct answer. A score of 0 is mathematically equivalent to abstaining, so just predicting the base rate of the underlying events.
But a negative score means the model's predictions are mathematically worse than just blindly guessing.
Yeah, a negative score means the agent is actively misleading you with false confidence. And looking at the results, the lack of calibration in frontier models is glaring.
Except for GPT 5.5, right?
Right. GPT 5.5 operating within the codex harness was the undisputed leader. It achieved 25% top 1 accuracy and a positive BSS of 0.05. It was reasonably accurate, and critically, it knew when it was uncertain.
But when the researchers evaluated other major models like DeepSeek V4 Pro, Opus 4.6, GLM 5.1, and Qwen 3.6 Plus,
many of them crash into deeply negative BSS territory.
Especially the open weight models. I mean, Qwen 3.6 Plus and GLM 5.1 were wildly overconfident and wrong when running their native default coding harnesses.
Right, but we need to separate the model's weights from the scaffolding it's operating in. Is the model inherently incapable of forecasting? Or is the native environment just poorly designed for a 90-day belief state?
That distinction is probably the most actionable insight for the developers listening today. A default coding harness is optimized for writing and executing Python scripts in a single session.
Exactly. It is not optimized for managing evidence over 3 months. To test this, the researchers built a custom baseline harness and applied it to the open weight models.
What specifically does this custom baseline harness do differently, though?
Well, it introduced three critical mechanisms. First, context consumption feedback. This explicitly tells the agent how much of its context window is full, basically forcing it to manage its own attention.
Oh, that's smart. What's the second?
Second is forced memory updates, requiring the agent to synthesize what it learned each day before advancing the simulation. And third, data frame loading.
Okay, explain the mechanics of data frame loading, because that seems like a massive shift in how the model perceives the text.
It is. In a native setup, an agent might just query the database and get back a raw, unstructured string of 50 news articles. It's overwhelming. Data frame loading allows the agent to pull that daily news into a structured pandas table using Python.
So suddenly, the model isn't just reading text, it's actually manipulating data.
Exactly. It can sort articles by publication date, drop duplicates, filter for specific entities, and even apply statistical functions to the task state before reading the underlying text.
It forces the model to structure its reasoning computationally rather than just semantically. And the results of that structural change were pretty massive, weren't they?
Very massive. When the open weight models were given this custom baseline harness, their Breyer skill scores flipped from negative to positive. The underlying intelligence, the actual model weights, didn't change at all.
But giving them structured tools to ingest data and reflect on their memory corrected their overconfidence. That perfectly highlights that raw intelligence does not equal agentic capability.
Right. If an agent doesn't have a structured framework to anchor its priors, it will simply hallucinate with absolute certainty.
But even with the improved harness, GPT 5.5 still led the pack. What specific capabilities actually drove that delta? The paper isolated a few key variables, didn't it?
Yeah, starting with search strategy, they compared two distinct approaches to gathering information. The first was full agentic search, where the model queries the local database every single day of the 90-day simulation, building context sequentially.
Okay, and the second?
The second was a single search baseline. So the model waits until one day before the event resolves and executes a single massive search query to find the answer.
That is the classic university student dilemma right there. Do you read a chapter every single day and adjust your understanding of the material incrementally, or do you try to cram the entire textbook into your brain the night before the final exam?
I think we all know how that usually goes. The ablation proved that cramming is a terrible strategy for test time adaptation. The single query method achieved an accuracy of only 14.2%. Yeah, but the daily agentic search achieved 31.2% accuracy. Forecasting complex events isn't just about finding the one article with the answer. It's about sequentially building a worldview and understanding the trajectory of the data over time.
But wait, if an agent is reading global news every day for 90 days, the context window would inevitably explode. How do they physically store and recall that chronological timeline without the model simply forgetting what happened in January by the time it reaches March?
They utilize file-based memory, so the agent writes summaries and probabilities to a persistent local file. And the ablation on this memory system reveals something really crucial about model behavior.
Which was what?
When they removed the agent's ability to write to these memory files, accuracy just plummeted. But it wasn't just a failure of recall. It was a failure to prevent hallucination drift.
Can you walk through the mechanics of drift? Like, why does the absence of a written memory cause the model's logic to degrade over time?
Sure. Drift occurs when an agent over-indexes on its most recent, immediate search results without anchoring them to past convictions.
Okay, give me an example.
Imagine the agent runs a search on day 10 and finds incredibly strong, well-sourced evidence regarding an election. It formulates a highly accurate prior.
Makes sense.
Then, on day 45, it runs a slightly different search and pulls up weak, noisy, or completely irrelevant data. Without a persistent memory to ground it, the agent will discard its accurate day 10 prior and heavily weight the new, noisy day 45 evidence, hallucinating a completely wrong trajectory.
So the memory file basically acts as an anchor. It allows the model to look at the weak day 45 evidence and computationally reason, okay, I have a highly confident, well-reasoned prior from a month ago. This new data point is weak, so I'm not going to alter my forecast.
Exactly. It forces the model to weigh historical conviction against new volatility.
But memory and search still rely on the model's baseline processing power. If we just give the model more time to quote-unquote think, pumping up the test time compute, does that solve the calibration issue entirely?
They tested that inference scaling by allowing the models to generate more reasoning tokens. So moving from none to low to high reasoning effort.
And did it work?
Initially, the returns were significant. Both accuracy and the Breyer skill score improved. The more time the model spent actively reasoning about the conflicting news reports, the less overconfident it was.
But there are diminishing returns, right? I mean, you can't just compute your way out of missing information.
That is the hard ceiling they hit. Moving to the absolute maximum setting, so X high effort, did not significantly beat the high effort benchmark for GPT 5.5.
Even though it was doing way more work.
Right. This is despite the fact that the X high setting consumed nearly 4,000 tool calls and 12.4 million tokens over a single simulation run.
12.4 million tokens just processing logic loops, writing code and verifying its own assumptions. That's insane. But if the geopolitical event hasn't happened yet, and the data simply isn't in the local Common Crawl database, thinking harder just leads to over-extrapolation.
Exactly. The model hits an epistemological wall. Additional compute cannot conjure facts that simply haven't occurred yet.
So we know the models can search chronologically, they can utilize persistent memory to prevent drift, and they benefit from scaled compute up to a ceiling. But how does this purely machine-driven intelligence compare to human collective intelligence? Humans have been aggregating information to forecast the future for centuries.
Well, to establish a baseline, the researchers actually mapped the model's predictions against real human betting aggregates on Polymarket, where thousands of individuals put actual money behind their forecasts.
And the data there is fascinating. On high-volume, highly objective events, GPT 5.5 didn't just follow the human consensus, it occasionally front-ran the market.
Yeah, the two prominent examples were predicting the winner of Super Bowl LX, where the agent tightly tracked the aggregate, and predicting the swearing-in of Nepal's Prime Minister Balendra Shah.
Oh, great.
In that Nepal market, the AI updated its probability distribution significantly faster than the human crowd.
But let's apply some scrutiny to that Nepal example for a second. The agent predicted the appointment of Balendra Shah by reading news articles about massive Gen Z protests. Did the model actually understand the causal relationship between a specific demographic protesting and a systemic political shift, or is it just pattern matching?
That's the big question.
Right, like is it just relying on its pre-training data, which dictates that the string Gen Z protests statistically co-occurs with new prime minister?
It's a critical distinction, but the simulation structure suggests actual sequential reasoning rather than static pattern matching. The model didn't start the simulation predicting Shah.
Okay, so how did it get there?
It required a daily sequential ingestion of the protest data over the 90 days to actually update its prior. It had to read the size of the crowds, the specific demands, and the timeline, and then computationally adjust its forecast higher day by day.
Oh, I see. That sequential updating process proves it is adapting to novel test time variables, not just regurgitating pre-trained associations.
Exactly. It's ingesting the geopolitical climate and updating a financial model faster than the slower, smoother curve of human intuition.
But it wasn't universally superior. Where did the models consistently fall behind the human aggregates?
The AI struggles significantly in markets that were subjective, preference-based, or reliant on unwritten social dynamics.
Can you give an example?
The two starkest failures were the market predicting the Grammy Album of the Year and a specific UK constituency election, the Gorton and Denton race.
Which logically checks out. Forecasting the Grammys isn't a data retrieval problem. You can't just read Reuters articles to figure out who the Recording Academy favors.
No, not at all.
You really have to understand the subjective cultural zeitgeist, the internal politics of the music industry, and unquantifiable public sentiment. A human crowd inherently understands those cultural vibes because they participate in them. An AI reading text simply lacks the context for subjective intuition.
Although the researchers did include a brief, compelling hint regarding multi-agent swarms at the end of the paper.
Oh, really? What kind of hint?
They ran multiple DeepSeek agents simultaneously, allowing them to aggregate their predictions, and saw early signs that the swarm approach boosted accuracy further. A diverse multi-agent setup might eventually be able to proxy some of that subjective nuance by weighing conflicting perspectives.
Okay, so for the ML engineers listening, building the next generation of agents requires moving well beyond static logic puzzles. This deep dive into FutureSim proves definitively that to build truly adaptive systems, just scaling parameter counts is insufficient.
Absolutely.
You need to focus intensely on continuous, long-horizon memory architectures that actively prevent drift. You need robust, hybrid search strategies that can parse evolving corpora. And you definitely need meticulously designed agent harnesses that enforce strict calibration through structural data manipulation.
And the data shows we still have a massive gap to close. The researchers identified what they call the upper bound gap.
Which is?
If you take GPT 5.5 and give it the specific forecasting question directly on the final day of the simulation, perfectly handing it all the necessary context in one prompt, it achieves 31.2% accuracy.
Okay, but what if it does it the hard way?
When that same model is forced to do it sequentially, managing its own memory, searching for its own context, and updating its priors over the full 90 days, it only hits 24.8%.
That 6.4% difference is the performance tax of sequential adaptation. Closing that gap is clearly the current frontier of agentic design. I want to leave you with a thought experiment based on these results.
Oh, like where this is going?
We just discussed a single GPT 5.5 agent operating in a custom coding harness that cost roughly $220 a month in API calls. And we saw that this single agent can sequentially digest global news fast enough to mathematically front-run human prediction markets on multi-million-dollar bets like the Super Bowl and international elections.
Right.
What happens when a quantitative hedge fund deploys not one, but 10,000 of these distinct agents, all running at high reasoning effort, dynamically reading every local newspaper and financial filing on Earth in real time, utilizing persistent memory to prevent drift, and structuring their findings through data frame manipulation before trading?
It's a staggering thought.
Will human traders even be able to compete on a fundamental level? Or will our global prediction and financial markets simply become a real-time measure of which AI lab has the most perfectly calibrated retrieval architecture? Keep that in mind next time you're evaluating a model's true capabilities. Thanks for joining us on AI Paper Podcast. We'll catch you on the next deep dive.